Hi, today we'll talk about the proofs, and we'll particularly illustrate the idea of how do we make proofs in predicate calculus using integers and some basic notions about integers. So first definition, we want to have, in order to write a proof, we have to have precise definitions. Otherwise, we cannot manipulate some verbal statements. So we need to usually have formulas, usually equalities, inequalities, so some mathematical objects that we can manipulate in a rigorous way. So generally what? So definition, n is even. So that's more verbal, and here in the definition we'll precisely using mathematical formulas of predicate calculus, describe what do we mean when we say that n is even. So n is even if there exists k from z such that n equals to k. So whenever we see this expression, we'll actually think of this equality. N is odd will always be treated there exists k from z such that n equals to k plus 1. So once again, this is verbal and this is formal. And whenever we see a statement involving one of these verbals, we always want to trade it for something that's formal. And the other definition, I will skip a few things from my notes that are just self-explanatory, by the way, or maybe I should. So, example, so 17 is odd. Why? Because, actually I can find the witness. So, because 17 equals 2 times 8 plus 1. So I found the witness, I found the k, so k equals 8, such that 17 equals 2k plus 1. And 14 is even, because 14 equals 2 times 7, where my k is now 7. And of course, natural question here is, question, can a number at the same time be even and odd? So that's a natural question. And let's see how are we going to prove that that will never happen. So the answer is no. And here's the proof. So, assume that a number, an integer n, is both even and odd. So the fact that n is even, according to definition, I can translate and say, oh, that means that n equals 2k for some k in z, for some integer k. But also, since n is odd, we can say, all right, n is also equal. Now comes the typical error. Very often people say 2k plus 1 for some k z. This is the wrong way to say it. Why? Because each of those two statements has its own witness, and no one says that that witness has to be the same. Once you call it k, you're actually claiming that there's the same weakness, and nobody said that, so you cannot assume something that's not there. So generally, in order to avoid that special assumption which is not valid, I will not call it k, I will give it a different name, I'll call it L. And why this cannot happen? Because here it is, I will compare these two lines and I'll get the following. If n is equal to 2k and n equals 12 plus 1, that would give me that 2k equals 12 plus 1. Then getting those even numbers on the left side, I will get 2 times k minus L equals 1. You see what happened? Here I had some statements that are hard to manipulate. You are never sure what you are concluding from there. Now we have equalities, which are important machinery that we studied, developed, and generally we are on much more solid ground trying to reach some contradiction here. Why is this not possible? Because we can say the following, we can say the following, which cannot happen. I'm actually here arguing by contradiction, and in section 2.5 we'll talk more about that type of proofs, which cannot happen because k minus L, if it is an integer, we have two cases. Case 1, if k minus L as integer is greater than or equal 1, then 2 times k minus L is greater or equal to 2, so it cannot be 1, it's too big. But then, case 2, if a number is, because you know how numbers go, 0, 1, 2, 3, 4, negative 1, negative 2. So if you are not greater than or equal to 1, you are in the second territory, less than or equal to 0. So you are there, then that's a blue version, and this was the red version. Now you are in the blue territory, so that means that k minus L is less than or equal to 0, but then 2 times k minus L would be also less than or equal to 0, so it cannot be 1. So that 2 times k minus L in red, because when you double it, actually what happens, that gap becomes bigger, because blue guys, when you double them, they give you a result that's 0 or below. Let's say blue. And the red guys gives you 2 or above. So nobody will hit. Oops, I need third color. Nobody will hit my number 1. Here is number 1. And that's why the same number cannot be, same integer cannot be at the same time even and odd. What else? In this section we also wanted to start talking a little bit more about prime numbers, composite numbers. So, and here's the definition. That notion is reserved for positive integers, and not only positive integers. One is excluded from that story, and you can see that from definition. So definition, let n be a positive integer greater than 1. So 1 is not in the game here. So what? We say that n is a prime if the only factors of n are trivial factorization. And then the same way we say that n is composite if, and then I'll quickly say if it has other factors, or I say if it has also a non-trivial factorization. So for example, 7 is a prime. Why? Because the only factorization of 7 is 1 times 7. But for example, 10 is composite. Because 10 equals 1 times 10, but besides the trivial, it also has, let's say, 2 times 5. So that's why that number is composite. All right, and then knowing these two definitions, we can now again illustrate a few statements that we prove about prime and composite numbers. So that's example 232. I'll try to squeeze it in here. Example 232. And the question is, prove or disprove that there exists n from z such that 2n squared minus 13n minus 7 is a prime. So generally, if you look at the logical structure of this statement, it's an existential statement. So we need to provide a witness. How do we find that witness? Maybe we can start, from 0 and go and hope that once we'll run into a witness, but it might be that that witness is far and we'll never reach it, or maybe it doesn't exist, so we'll never know. So we'd like a little more organized search. So generally, this problem gives us a chance to solve it because this expression has some special structure. Why? Because let's look at the expression, even if we don't know a solution, even if we don't know what n is, this quadratic expression has a nice and easy factorization. What would that factorization be? N minus 7 times 2n plus 1. Of course, you can ask, how do we know that that's a factorization? For example, there are also some methods from intermediate algebra, how do you factor quadratic expressions. For me, the simplest one is just solve quadratic equation and use factorization theorem. So generally, 2n squared minus 13n minus 7 equals 0. If you solve quadratic equation, you get 13 plus or minus square root of 169 plus 56 over 4, which would be 13 plus or minus 15 over 4, which would be 28 over 4, which is 7, or negative 1/2. And then this factors out as 2 times n minus 7 times n plus 1/2. Factorization theorem says if you have a 0, you have n minus that 0 factor and the other one, and 2 is the leading coefficient. And then if you multiply by 2 here, you see with that 2 on the second factor, you exactly get this. Anyway, this is less important than the algebraic part, but probably you're curious, how did we know to do that? So let me exclude that. So question is what? So most of the numbers will be composite in this, most numbers in this form will be composites. Why? Because here's a factorization. And the only way to make this prime is to force one of these two numbers to be 1. So in order, and that might not help, But if you don't force any of them to be 1, then here's your non-trivial factorization and your number is composite. So let us try to force one of the factors to be 1. So who could be 1? So either n minus 7 should be 1, or 2n plus 1 should be 1. This one will not give us anything. Why? Because it's very easy to see that when 2n plus 1 is 1, then n would be 0, then n minus 7 would be negative, and then negative number is not a prime according to our definition, so that will not work. So basically what it tells you is that our only hope is n equals 8. So if n equals 8, why am I saying it's only our hope? Because yes, you made this factor 1, but nothing guarantees that the second one might not be on its own composite number. So we'll see. But what we wanted to say is nothing else but 8 would work, because whatever else you try, you will get either negative number or you will get something that has non-trivial factorization. So let's see what happens when n equals 8. When n equals 8, we'll get what? 2n squared minus 13n minus 17 equals 1 times 17, which is 17, which is a prime. So here it is. So we actually found our witness. So the answer is yes. A witness is n equals 8, and the statement is true. So if it's existential statement, then one of the straightforward proofs is just to find in the witness